Hello my friends, this is part 2 in a series of videos on why Cohen's D is so important to report when you're doing a t-test. And what I'm going to cover in this part 2, this is going to probably be a fairly short video. I've just got a few more things I want to mention. And what I want to emphasize here is variability. The importance of the variability of the scores. Very, very important to be aware of this. So let's learn about how variability affects p-values in Cohen's D. All right, we're going to learn about this using a concrete example. On the left are the scores that I've been using in part 1 of this series of videos. These are self-estimated IQ scores. They're hypothetical. I just made them up. For males and females, we see that the males are estimating their own IQ to be higher than for females. A little bit higher. They're averaging 116.2, females 110.2. So another word for average is mean. So the mean score for males is 116.2, the mean score for females is 110.2. Now let's say I do another study. Another study meaning I just get 5 more males and 5 more females. I just replicate the study. Let me try it again. So I get 5 more males and 5 more females. And again, whoa, this never happens, but hypothetically, I get exactly the same mean, 116.2 for males and exactly the same mean for females, 110.2. Now you might say, oh my God, I got exactly the same results. Amazing. Actually, there's something important that's different. The means are the same, but there's something different. If you want, you can pause this video and start it up. Look at those scores. Yes, the mean for the males in both studies is 116.2. Yes, the mean for the females in both studies is 110.2. But there's something very important. Very, 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 very important. The mean is not everything. Can you see what it is? If you didn't see it, once I tell you, it's going to be obvious. You're going to go, oh, duh, why didn't I see that? What's different about the results in study 2 from the results in study 1? Okay, again, you can pause this. I'm going to go ahead and I'm going to tell you the answer. The answer is that study number 2 has less variability. They're closer to the mean. In study number 2, the male scores are varying from 114 to 118. They're extremely close to the mean of 116.2. They hardly vary at all. They hardly vary at all from the mean. Whereas in study 1, there's higher variability. Same thing for the females. With the females, in study number 2, ranges from 108 to 112, staying very close to the 110.2. In study 1, more variability. So study number 2 has the same mean scores, but much less variability. Now, does less variability make us more confident or less confident, or does it change our confidence? Once I explain it, again, it'll be obvious. Is it good to have less variability? The answer is yes. Less variability means that your results are more impressive. You are much more confident that there is this difference. If I get the results in study number 2, I'm much more confident that males think their IQ is higher than females do, even though in reality they're not different. Why would I be more confident that males overestimate or females underestimate their IQ? I can compare to their actual IQ to find out which it is. But males think their IQ is higher than females when it isn't by 4 points, from 6 points, from 110 to 116, and I'm much more confident. I'm much more certain that males score themselves higher than I am from study 1. And we can look at the p-value and look at the p-values. I ran the t-test on these 2 sets of scores, and for the For study number 1, I mentioned in part 1, the p-value is 0.30. Well, 0.30 is it's not statistically significant. It gives us very little confidence. The second study, the p-value is less than 0.001. Fantastic. We've gone from extremely low confidence to extremely high confidence with the same difference in the means. And if you think about it, I mean, it makes sense. I mean, just look at it. The highest score for females, in study number 2, the highest score for females is 112. The lowest score for males is 114. That means the female who estimates her IQ at the very highest is still lower than the male who estimates his IQ at lower than any of the other males. All the males are higher than the females. So, I mean, you don't have to be, a mathematician to figure out, like, oh my God, all the males are higher than all the females. It looks like they really think their IQ is higher. Yes. Less than 1 out of 1,000 would you get this. Whereas this, 30% of the time you replicate the study, you'll get those results. So variability, I just want you to know about variability. Variability is measured in 2 ways. It's called variance, and then you can take the square root of the variance, and it's called standard deviation. Now you might have heard this term, standard deviation. If you haven't, you need to. From a nerd standpoint, you've been living under a rock, man. Standard deviation, really, everybody should know what standard deviation is. It's a measure of the variability. So when the standard deviation is small, it means the p-value is going to be higher. Probability of getting these results, much less likely. We have much greater confidence. The effect size might not change at all or very slightly, but you're able to detect that difference with much greater confidence. And the wonderful thing about the statistics, it just tells you, man, this is what it is. This is the likelihood. You don't have to sit there and look at it and say, that looks like a lot to me. It just tells you. So it's very, very cool. And look at Cohen's D. Cohen's D is a measure of, it's actually a measure of the difference of the variance, of the means. It's a difference of the means measured in standard deviations. It's similar to a z-score for individuals. Well, if you don't know what a z-score is or any of that, maybe I just threw a bunch of fancy words out there. But it's just a very handy way to measure. Well, I'm going to show you on the next slide. I'll show you what I'm talking about. It's a way of measuring how different these are. So Cohen's D goes from 0.697 to 3.6561. Actually, 0.7 is already strong. 3.651 is huge. So that means when Cohen's D is large, that means that there is very solidly this difference. It's very clear that there is this difference. Okay, so some conclusions that we have are that t-tests, conclusion from part 1, t-tests are more useful than sometimes recognized. I talk about this in part 1 of this 2-part series, that a t-test, you can use composite scores, you can use uncorrelated or weakly correlated variables. You can make, things like a health score, an IQ score, all kinds of things that you can take a collection of variables, combine them together. You can use what we call regression models, all kinds of different things. You can combine them together and get something that you're comparing. So that's a really cool thing about t-tests. And the big point we're emphasizing here is to report both the p-value and Cohen's D. Also nice to report, I don't mention it here, is the proportion of the means to each other. Divide the experimental group mean or the treated group or a lot of times there's no experiment, or just the one that's higher divided by the other one. by the lower one. And that shows you the percent increase in the mean. So actually 3 things good to report. P-value, Cohen's d, and the proportion of the means. The larger mean divided by the smaller mean, for example. The larger mean divided by the smaller mean. It's a good way to just consistently do it that way. Larger mean divided by the smaller mean. Large mean divided by the smaller mean. And I showed that in part 1, an example of that. And Cohen's d. So those 3 things are good to report. Now, Cohen, when he came up with this, he said 0.2 is low, 0.5 is average, 0.8 is high. Using those scores, even this 0.7 is very good, and 3.651 is huge. So you're getting a much better Cohen's d. Now, here's what Cohen's d tells you. What Cohen's d tells you is this. I'm going to make this very concrete. It tells you how much overlap there is in the distribution of scores. So here we have the height of females and males. The gray is the females, the pink is the males. The males are a little bit taller. But everybody in this area, the dark, where the gray and this pinkish color overlap, makes this kind of like burgundy color. Those are cases where there are both males and females. Whereas out here on this right edge, it's mostly just males, and on this left edge, mostly just females. So it's telling us what the overlap of the distribution is. So Cohen's d takes the difference in the means, but looks at the entire distribution of it. Whereas if you compare the means, suppose you compare the mean, the peak of each one of these. But what if this distribution was very skinny? If it's very skinny, comes almost straight down, that means there's lower variance. With less variance, there's less overlap. So Cohen's d is telling us how much overlap there is in the distribution, is one way to think of it. So it's a very good measure of how much the scores are different from each other. How much are they not overlapping? So that's what this, and here on this website, let me show you this website. I forgot to, I lost it. I'll bring it up. Sorry. I'll bring this up. Let me show this to you. Okay, so here is, that's fine. That's good enough. What is it? I'm going to type it in, lbecker.uccs. Let me see if I can type this in properly. Sorry, this will just take a second. If it takes me too much, I'll just remake this whole video. Becker. Oh, good. I've already got it in there. So here's this website from University of Colorado in Colorado Springs. I think it was, when you expand, I think it was the second section. Yes, there it is. So I found it. So here is Cohen's d. And what it's telling us is that Cohen's d is small, 0.2. See, it's a small, medium, large. Then the percent of non-overlap is only rounded off 15%. Whereas if you're 0.8, it's 47%. So with the large p-value, those distributions are not overlapping. And the other way you can think of the p-value is this. I'll highlight this as an example. An effect size of 1.7, if we look at 1.7 over here, indicates that the mean of the treated group is at the 95.5 percentile of the untreated group. So that 95.5, what this is telling us is out here towards this edge is like the 95 percentile. So it's telling you where the mean of the treated group, that means the larger one essentially, where it's falling as a percentile. Because as you go further out to the right, head to the right, the percentile, the percentage of people to the left is greater, right? I mean, as you move to the right of this curve, there's more and more people that you've passed. When you're out here, 98 or 99% you're at the 98th percentile. Your score is higher than 98% of the people. So it's a way of stating where this peak is of the group that's larger in relationship to one that's lower. So this just gives you an idea that Cohen's d is about tells you how much the distributions are overlapping. That's what it's telling you. And if they're not overlapping, it means they're really different. It's a measure of overlap. So that's what it is. And a nice way to think about it is the way Cohen described it, which is, if it's 0.2, that's small. There's only 15% of the data is not overlapping. Medium, 1/3 is not overlapping. Large, almost a half are not overlapping. Now, in some research, like in the research I do in the field of astrology, very little has been discovered. If we can even get 0.2, a 15% non-overlap, we're chipping away at something. Now, here's another thing that's really important. Some research in astrology, astrology is very controversial, and people will say, oh, I got a 0.01 significance. I found a difference. Well, okay. We also want to know the effect size, because if you did it on 2,000 people, which is often the case, in some of these research studies, many thousands, the actual difference could be extremely tiny. You're able to detect tiny differences. But you might still say, well, at least in theory, you found something. But let me mention this about p-values. When we say 0.01 is statistically significant, there are assumptions. Everything in research has assumptions. One of the assumptions, this is huge, drum roll, lights, action, camera, this is really important. A big assumption of p-values is that you've done a hypothesis test, a strict hypothesis test. That means you stated what you expect, then you look at the data you look at the data after you've stated what you're expecting, and then it's confirmed. A strict hypothesis test. What a lot of researchers do when they're not properly trained in research methods, they try this, they try that, let me adjust this, let me look at it this way. Every time you do that, it's called a Bonferroni correction. Every time you look at another thing, you have to reduce your probability. So if you're getting 0.01 probability, but you looked at 10 different things, no, you don't have 0.01. 0.01 is impressive if you've only looked at one thing. You had a hypothesis, you looked at that. Now, we want to do exploratory research. Sometimes you're doing research, you have 10, 20, 30, maybe you're not even sure what you're going to find. That's what machine learning, data mining, all these fantastic, wonderful things. So I'm not saying you shouldn't explore, and I'm just saying when you do the statistical tests, you have to be aware of what you're really doing. So what a lot of people are doing, if they're not properly trained and they're not supervised at an academic level, is they're doing multiple ideas and they're saying, I got 0.01. That's not impressive. It's not a real 0.01. 0.01 is a strict hypothesis test. Okay, so we've learned some key things. If you watch both of these videos, you've really learned a lot about what a t-test does, how to think about it, how to think about probability, the p-score, how to think about Cohen's d. So these are really important things. And even if you're not a researcher, I think it's really important. Like I mentioned in the first video, I watch health videos on this vitamin, this mineral, and even medical doctors constantly quoting the p-value. And sometimes they'll do something like this. They'll say, oh, in this study of, say, garlic or something, the garlic didn't work very well. The p-value was not significant. on all 20, they did 20 people. 20. Did you say 20? 20? I mean, if you have only 20 cases, getting statistical significance is very difficult. You have to have a large effect size. Then they'll quote another study and they'll say, well, this other thing studied something else and it really works. It got a p-value of 0.01. And they studied 1,000 people. Whoa. One study did 1,000, the other did 20, and you're comparing the p-values? No. You can get a much better p-value with a larger number. We call that n, the sample size. If there's an actual effect size, you will detect it with a larger n. So all studies are good. You just have to realize, they're good conceptually. If you have only 20 cases, you have only 20 cases. If you have 1,000, you have 1,000. Research is very practical. And if you have 1,000, you're going to get much, much greater confidence. But studying 20 people is better than studying none, So it all depends on your circumstances, your situation, what you can fund, what you have time for. What's really important is to know how to properly report what you found. That's the key, to honestly do it. You have to know some basic principles. If you understand all the principles I presented in this two-part series of videos, you have a pretty good foundation for being able to look at research results and think about them. And you have a really good start, and you understand some of these basic concepts. Let me see if there's anything else I wanted to say. I think that pretty much covers it. Yes, that's it. So I called this two-part series, Why Cohen's D is Important to Report, or something like that, because we need to know about the effect size, not just the probability. And I've covered a lot more than that. We've covered about the importance of variability and other things that affect your research results. And most of these principles apply to other kinds of tests as well. It's not just t-tests. There's ANOVA and chi-square and blah, blah, blah. It goes on and on and on, all kinds of stuff. And you even will do t-tests or other kinds of tests within the context of data mining and all kinds of things. So there it is. Now, if you're a subscriber, I want to thank you so much. If you're a member, oh my God, thank you. And members, starting in February 2024, I'm going to have a live monthly meeting for members only. So if you click on the link to the members, underneath the description if you go to my channel, if you're at my channel, go to my channel, my YouTube page, you'll see underneath the description, I recently just put it there, so it's easy to find, is the link to join. And there's 2 membership levels. If you want to meet once a month with questions and answers, or the other option is twice a month meetings. And if you can't make it at the time of the video, then they are recorded for the members. Okay, that's it, my friends. Thank you very much for listening. God bless. Namaste.